So we're going to continue on in our practice or our guided notes, and you'll notice that we're going to be moving to sample problem 4.2 on page 166. So that's what I pulled out here. So sample problem 4.2 is a beam, okay? And the beam has 3 loads on it. It tells us that the load at P, although it's not identified here, in the problem it says that P is 15 kips. And then we've got 6 and 6 to the right side. And then it's being supported at A and at B. At A, this is going to be a roller. And at B, this is going to be a pin. What I'm going to have you do is I'm going to have you draw the free body diagram. Just use a regular line for the length of the beam. And then draw what you believe the reactions are at the supports A and B. And then we'll compare. Okay, I'm going to give you a chance to kind of think about it, put some stuff down. Even if you're not exactly sure, we'll talk it through, but just give it a shot. Okay. So I'll give you about a minute and then I'll start sharing what it should look like. And then P is 15 kips, just so you know. Okay. I'm going to zoom out a little bit here, and we're going to start drawing the free body diagram here. So I'm going to add my convention so I don't forget. Page 166, we're on sample problem 4.2. And I'm going to draw my beam from A to the end. A is going to be here. B is going to be about here. Okay. Then I've got P coming down. And they said that's 15 kips. And then I've got 2 forces out on the end here. 6 and 6 kips going down. Okay. And then distances are 3 feet, 6 feet, 2 feet, 2 feet. Those are my applied loads that are given to me. And then the distances. Now, A is a roller, right? A roller, we look on page 160 at the top here, 1 force, and it's always going to be perpendicular to the surface it's riding on. Now, since the 3 forces are down, the applied loads, I am going to assume up, okay? I don't know, my math will tell me, it'll confirm, right? If I end up with a positive value at the end, it'll confirm, and we'll call this AY. The force at A in the Y direction. And then I have another at B, okay? At B, I've got a pin. So a pin reaction is going to have 2 forces, an X and a Y, because it goes horizontally, right? It stops any motion going horizontally and vertically. It can't move. Okay. So here I'm going to show a vertical force, and then I'm also going to show a horizontal. Okay. So I'm going to kind of put it a little bit offset, but it's along the line here. So I'm going to show my BX going to the right. And my BY, I'm going to show going up again, just because the other applied loads are going down. But again, if you assume a different direction, just know that you'll confirm or disprove it as your final answer. Any questions on the free body diagram? Free body diagram. Okay. Then once we have a good free body diagram and we have all the information we need, we have everything labeled, identified, dimensions. Now we're ready to use our equations of equilibrium to solve for the unknowns. We've got three unknowns, the AX, AY, I'm sorry, the AY, the BY, and the BX. Okay, so our step number 2 is going to be our equations of equilibrium. Okay. So as we look here, where do we want to start? We have 3 of them. Some of the forces in the X equals 0, some of the forces in the Y equals 0, and some of any moments are also going to equal 0. Let's do X, Josh says. Okay, let's do X. So we're going to sum our forces in the X direction equal to 0. Remember, I have to see what you're going to do. You have to show this in variable form first. So I'm going to look, I've got a BX, that's it, right? So I'm going to say BX is equal to 0. And it is. There are no opposing forces for that support in the X direction, but you need to tell me that X component, and sometimes this will happen, that there is nothing that's going to be equal to 0. Now, the reason you need to tell me that is, for instance, on a shaft, we can simulate it like a beam. And there's going to be forces on a shaft when we have our machine elements class, which is going to be next a year from now, which you guys will have. And then we're going to have bearings that are going to support those forces along the shafts. And those bearings are going to be like simple supports as we see here. And the bearing, if it has an X component value, that means that there's a side load on that shaft. And then now we're going to have to look at different types of bearings that can take side loads. So we always have to identify if there's a force like we see here, we call it an axial force. It's along the axis. Okay. All right, what are we doing next? So we've got our X solved for. We know this to be 0. Okay, but we still have to show it. We still need to calculate for it. What are we going to do next? Yeah, let's sum the forces in the Y. Yeah, let's do that. So I'm going to do that right next to it. Sum the forces in the Y equals 0. And I'm going to start left to right. I've got a positive AY. I've got a minus 15 kips going down. A positive BY. A minus 6 kips. And a minus 6 kips, right? And I'm going to set those equal to 0. So I'm going to combine what I can. It looks like I've got 12 and 15, that's negative 27. So AY plus BY minus 27 kips is equal to 0. I'm going to put the negative 27 on the other side. So I'm going to have AY plus BY is equal to 27 kips. Okay. That's okay. I'm set up now, right? So I have one more equation of equilibrium that I can use. So we're going to sum our moments, right? What point do we want to go around, A or B? A, sure. Or B. You could do either one, all right? I tend to start on the left because that's the way you kind of read, right? Let's sum our moments in the A, or sum our moments around A to then solve for our BY. So sum moments around A equal to 0. And I'm going to kind of go back and forth, but I want to be sure you can see this. So I'm going to put my finger on A. And I'm going to start with the 15 kips and see if it causes rotation. It does. So I'm going to take 15 kips times its perpendicular distance from A, which is 3 feet. And then when I pull in this direction, it's going to go clockwise. So a negative out front. So 15 kips times 3 feet, negative out front. Put my finger back on A. And now I'm going to push in the direction of BX. Notice that, well, it's 0 anyway, but it wouldn't cause any rotation. But my BY will. My BY is going to rotate counterclockwise, so that I'll be positive out front. And we're going to take BY times 9 feet. Negative out front. Finger back on A, and now I'm going to do my 6. That's going to be clockwise, and its distance is going to be 8 plus 3 is 11. So 6 kips times 11 feet, and that's going to be negative out front. BY is positive, because that's going to go clockwise, counterclockwise. So BY is counterclockwise, and then the other two are clockwise. They're negative. Then my last one is the 6 kips. So it's going to be 13 feet. And negative out front for that one as well, because it's going to go clockwise. So that takes care of all of my forces. I set this equal to 0. I combine what I can, and I'm going to solve for BY. So go ahead and do that. Check my work as we go here. It's 30. You should get BY equal to 21 kips. We ended up with a positive value, no lingering negative. So that means that our BY's direction is confirmed. Okay. So that one's done, right? So all we have is AY. So now we can take this BY, we can put it up into some of our forces in the Y direction equation and solve for AY. And I don't have enough room here, so I'm going to kind of bring this down over here. I'm going to say AY plus 21 kips is equal to 27 kips. Okay. I'm going to subtract on both sides. So my AY should equal 6 kips. Which if we look in the book, it confirms, yep, everything is the same. Any questions? Kind of fun, not hard, just kind of a reapplication, but now applying that condition of equilibrium, okay? All right. Virtually, any questions from you guys? Everything look okay? Makes sense? Hopefully. Okay, let's do another one. Let's do another one. So let's turn the page. And we're going to look at sample problem 4.3. Sample problem 4.3. Sample problem 4.3 is found on page 167. Okay. Now, in this case, we've got a loading car is at rest on a track, forming an angle of 25 degrees with vertical. So here's the 25 degrees. The gross weight of the car and its load is 5,500 pounds, and it is going to be directed and here at the center of gravity. Okay. And then it's going to act 30 inches in from the surface it's riding on. And it's going to be pulled with a cable that is 24 inches from the surface it's riding on. They want us to determine the tension in the cable and the reaction at each one of the wheels. Okay, each one of the wheels. So what we're going to do is we're going to rotate this a little bit. Okay. And the reason we're going to rotate it is because all of these things are perpendicular except one thing, the weight, to that 25-degree angle. So what we're going to do is we're going to take this and we're going to make this horizontal. Okay. And we're going to draw the free body diagram with the tension here, and we're going to go straight through the tension, 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 and we're going to offset our center of gravity 6 inches. Okay, because it's 24 and then it's 30. So there's a difference of 6 inches between the center of gravity vertically and the tension in the cable. Okay, and then we're going to show each one of these. So it'll make more sense when I don't know if maybe it makes sense now. I think it makes sense now. Put our convention in place. Oopsie. And we're going to draw our straight line. And the straight line is going to represent the point where the tension, the cable, where the cable attaches right here. We'll call this point C. Okay. And then we've got an A. Does it matter? I'm just trying to think. I don't think it really matters. We're going to put A here. And we'll put B here. Okay. And then our G is going to be between here, but it's going to be 6 inches up. Okay. 6 inches up, because remember, from the surface, it's 24 to our tension in our cable, which is going to be right here, and then 30 up to the center of gravity. Now, I'm going to draw a line kind of through here to represent horizontal. Now, as we remember, our weight of the 5,500 is going to be through the center of gravity here. See, I'm going to tip this up because see it a little better. So we can see that we're going to represent that 5,500 going straight down. Okay. Now, because we are taking this and we're tipping this so that this is horizontal, do you see how the 25-degree angle is going to be right there to the horizontal with the center of gravity, with the weight? Okay. So that means that our G is going to be like this. Okay. From that point. And this angle right here is 25 degrees. Make sense? So now, because that's not on the X or Y, what do we get to do? We get to do the components, right? We get to do the components. So here is our Y. This is going to be GY, and our GX is going to be here. And then our G, right, point G, is going to be 5,500 pounds. Okay. And then we'll add a couple dimensions yet too. So we know that the dimension between here and the line between A and B is going to be 6 inches. Okay. We know that the distance between A and G, okay, is going to be 25 inches. And then the distance between G and B is also 25 inches. Now, the force at C, we don't really need to know this difference because we're going to find out that it's a horizontal force, so it's not going to end up having an effect. So we're just gonna show how we can make it clear. So we're just gonna show C going in that direction. We're just gonna call it C. All right. That's the tension in C. That's the tension in that cable. So this is our free body diagram. All right. So this is one free body diagram. So step number 2 then is going to be using those equations of equilibrium to solve for the reactions at A and B. Now, and the tension in the cable. I forgot to put A and B in here, so let's put A. It's gonna go this way, so that we're gonna call this AY. And B, it's gonna be here, because it's a roller, BY, right? Because those are two wheels, A and B. Oh, I forgot one other thing. What else can we calculate here before we worry about equations of equilibrium? Yeah, GX and GY, so those components, right? So go ahead and solve for the GX and the GY. Notice that our 25 degrees is in our standard place to use the cosine for our X and sine for our Y. And when we're talking about thousands of pounds, I don't think we need decimals of a pound, so I just went to the nearest pound. So I got GX is 49.85 pounds and GY 23.24 pounds. Now we're ready to use our equations of equilibrium to solve for C and AY and BY. Why don't we call this CX? So we know that it's not a point. I'm going to call it CX because it's in the X direction. All right, equations of equilibrium. Where do we want to start? We've got three of them. Sum the forces in the X, Josh? Sure. So sum the forces in the X direction equal to 0. So as we look, we've got a negative CX and we've got a positive GX, but we know GX to be 49.85, right? 49.85 pounds is equal to 0. So we can say that, we can put that to the other side, negative CX is equal to negative 49.85 pounds. Both become positive. Remember, don't leave any negatives. I like to keep my variable on the left, so I usually will push the other on the right. If you kept the 49.85 positive and pushed the CX to the other side, that's totally fine. Totally fine. Okay. So we've got our CX solved for, right? We know that to be 49.85 pounds. Good. Now what do we want to do? Two more. Sure, let's do sum the forces in the Y. I'm going to do it right next to this over here. So sum our forces in the Y direction equal to 0. We've got a positive AY, it's going up, a minus GY that we know to be 23.24 pounds. And then we have plus BY, right? Plus BY. So those are our sum of our forces in the Y, and we set that equal to 0. And now I'm going to put that to the other side. I'm just going to say AY plus BY is equal to 23.24 pounds. And we just need to stop there for right now. Now what? Our two unknowns are AY and BY. Probably got some moments, right? Around A or B. A, you want to do A? Sure. Or B, whichever one. We'll sum around A. So I'm going to sum moments around A equal to 0. Put my finger on A. Now, this is where this distance doesn't matter because CX runs right through A, right? So it's not going to cause rotation, so we don't need that perpendicular distance. They didn't include it either, all right? But when we go to GY, that is going to cause rotation, okay? So our GY magnitude is 2324. So 2324 pounds times perpendicular distance. GY is right here. So the perpendicular distance is 25 inches. You see that? 25 inches. Okay. GX is offset. GX is 6 inches above A. It will cause a rotation. Okay. It's not going to pull. It's going to actually cause rotation. So GX is 4985 pounds times its perpendicular distance. Pull it back along its line of action. That's the 6 inches. Okay. And then inch symbol, because that's what I was using. And then direction of rotation is going to be negative. Oh, I didn't put the sign out here. Let's do the GY. I'm really being forgetful. That's negative as well. So negative out front, both of those. The GY component, which is this one, and the GX. They're both causing a negative rotation. And then our last one is going to be BY, right? BY. So BY times 50 inches, and it is going to rotate positive. Those are all the forces causing rotation. So we set that equal to 0. Equal to 0. So go ahead and solve for BY. So your BY should come out to be 1760 pounds. And now we can plug that BY to solve for AY, right? Put BY up here. So AY plus 1760 pounds is equal to 2324 pounds. And then we're going to move that to the other side, subtract it off. So 2324, 1760 minus 564 pounds. Notice that each one of these values came out positive, so the directions that we assumed were correct. All right, what do you think? Kind of got it? Feel good about it? Probably the biggest challenge here is just getting used to making sure that we're setting up the free body diagrams properly, okay? Getting all the forces that we need, known, unknown in there, all the distances, all that kind of stuff, okay? Good, 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 good. Let's see where we're at problems-wise. Let's do one more problem tonight. And then what I want to do is I want to leave some time that if you have any questions on module 4, you have the opportunity to ask. So let's do one more practice problem. This will also get those who are ready to start working on module 5. You'll have some practice here that I think you'll start to, you'll have confidence to get started on that if you wanted to. All right, so this is problem 411. This is on page 176. So this is going to be back in the problems portion of the book. And this is 411. All right, here's 411. The problem is right here. The statement is on the right-hand side, okay? So it says for the frame and the loading shown. So I'll zoom in here a little bit so you can see it for those who might not have the problem in front of them. Determine, you guys, determine the reactions at A and E. So E is a roller, A is a pin. When alpha is 30 degrees and alpha is 45, I think we're just going to do this once. We're not going to worry about part B. We're just going to do part A. That'll be enough. Okay, so alpha is going to be 30 degrees. We want to determine what are the reactions at the two supports. Okay, so we got to draw our free body diagram, right? So we're going to draw it starting at A, going over to B, coming down to C, down to D, and then over to E using the dimensions and the angles that they have here. So go ahead and kind of get it in the form we see there. Okay. Don't forget your convention. Start with A to B. I think so. This is D. D. So I have all my applied loads in and my distances. And I have points for my reactions at my support. So I'm going to add those in just a bit. Now, as we look at A and at C, okay, you're going to notice that A is a pin and E is a roller. So let's do A, the pin first. The pin, as we know, is always going to be an X and a Y. There's always two of them. So we're gonna represent an X and a Y here. Now, again, we don't necessarily know the exact direction, but we're going to assume a direction. So I'm going to assume AY going up. And since I have an X directed force here going to the left, I'm going to show AX going to the right. Okay. And then E is a roller. Now the surface it's riding on is 30 degrees from horizontal, right? So that means we're going to be perpendicular to the surface that it's riding on right here. Okay. And that's going to be like E. So that means that there's going to be an EX component, right? An EX. And an EY. Now, angles, right? Angles. Where's my 30 degrees in here? Is it here or is it here? You see it? Take a guess. We know this is 90, right? This is 90. If I move this up along its line of action, this is 90. I don't know if that helps.
At the bottom. What?
I don't know. What do you think? Or is it here? What was that?
I think you got 6.
For which one? This one's 60 or this one's 60? I don't know. This is 90 degrees right here, right? 90 degrees. So if this is 30 of it, right? This would be 60. You're correct. This would be 30, right? Does that make sense to everybody? Do you see that? Okay, you got to be sure you know how to do this because these are, you're going to come across them that are going to be at angles like this. This is 90, 30 of it is here, 60 would be here, 30 is here. So our 30 degrees is here or here, right? This is the other 30 degrees. Meaning this angle right here, right? Now, because E, we have to resolve that into its components, right? Now, we don't know what E is, but just kind of think ahead with me here for a little bit. If we try to sum our forces in our Y, we've got two unknowns, right? AY and EY. If we try to sum our forces in the X, we've got two unknowns, AX and EX. Those are not the same two unknowns, right? But if we get EX and EY in terms of their hypotenuse, now we only have three unknowns and we can deal with three with our three equations. Does that make sense? We have four unknowns, otherwise we don't have four separate equations. We need three unknowns for three equations. So what we're going to do is we're going to resolve EX and EY into its hypotenuse. We've done this before, okay? So let's do EX is equal to, so if the 30-degree angle is here, right? 30-degree angle is here. To get EX, it's going to be the side opposite over the hypotenuse E. So EX is going to be equal to the side opposite. That's going to be the sine of 30, right? Times E. Everybody see that? Because the 30 is the side opposite from our EX. Our EX is right here. It's the horizontal component. 30 degrees is here. It's the side opposite. Here's the hypotenuse. So if we take 30 sine, that's 0.5. EX is going to be equal to 0.5 times E. Okay. Our EY is the side adjacent to the 30, right? The side adjacent. So that means EY is going to be the cosine of 30 times E. So 30 cosine 0.866 times E. So instead of writing EY, we're going to do 0.866 times E. And instead of writing EX, we're going to go 0.5 times E when we need to. Okay, so diagram done. Okay. Now we're going to use our equations of equilibrium to solve for AX, AY, and E. What do we want to do first? Sure, let's sum our forces in the X, see how far we can get. So sum the forces in the X direction equal to 0. I know I'm going to take some room. I'm going to actually start over here on this side because I've got some room up here. So I'm going to sum my forces in the X direction equal to 0 here. So only horizontals. I've got a positive AX. I've got a negative 20 pounds. And I've got a positive, not an EX. I've got a 0.5 E. Okay. Positive 0.5 E. Equal to 0. So I'm going to put my 20 to the other side. I'm going to say AX plus 0.5 E is equal to 20 pounds. And that's where I'm going to stop, right? For right now. Okay. Now what do I want to do? Sure, let's try the forces in the Y, see how far we can get. So sum forces in the Y equals 0. So we look at everything vertical. I've got a positive AY, a minus 20 pounds at B, because it's going down. And then I've got a positive EY, but I'm going to write a positive 0.866 E equal to 0. Now you might say, oh, I've got two equations, two unknowns. No, you don't. We've got AY and AX, not A's. So we can't do our substitution method at this point. Right. So we've got one equation left, right? Where are we going to sum our moments around? A or
A.
E? What did you say?
Point A is easier.
Yeah, let's do point A. It usually is. A is a favorite. All right, so I'm going to leave a little room underneath here in case I need, and I know I'm going to have to go back. So I am going to sum my moment around point A equal to 0. So we're going to put our finger on A. That gets rid of two of our unknowns, which is really smart. And now our only unknowns are going to be, our only unknown is going to be E, because we're going to write EX and EY in terms of E. Okay. So I'm going to start over here with my 20 pounds. Okay. Cause rotation. So 20 pounds times perpendicular distance of 10 inches. Okay. And it is going to rotate clockwise. So negative out front. My next one is going to be my 20 pounds at C. It is also going to rotate in a clockwise direction. So that'll be negative. So 20 pounds times. Now perpendicular distance here. Let's bring it all the way over. And its radius is going to be 3 inches. You see that? Yep. So this distance is going to be 3 inches. 20 times 3. And we saw that it was going to rotate clockwise. So negative out front. Okay. So 20 times 10, 20 times 3, both are negative out front. And then we have E to deal with, right? So we're going to put our finger on A. Let's start with EY. EY is offset. It's going to cause a rotation. Now, this is where we got to find our distance. So we have 8 here and then 3 to B. So it's 13 all the way back to A. So 13 minus 8, what would that be? 13 minus 8, is that 5? Yeah, it is. I don't know why 6 was popping in my head. I'm like, is that right? It is. So 5 inches from the EY. So remember, our EY is 0.88 E. I'm sorry, 0.866 E. That's the magnitude of EY times its perpendicular distance is 5 inches. Okay. And when we go and we rotate, it's going to be going in a positive direction because it's going to go counterclockwise. So does everybody see that? So it's negative 20 times 10, negative 20 times 3, and then a positive 0.866 E times 5 inches. So this right here is EY. That's EY. All right, we still have one more force. We've got EX, right? So finger on A, direction. This is going to cause rotation going counterclockwise. So it's gonna be EX, but instead of EX, we're gonna write 0.5E. So down here, I'm gonna add 0.5E. This is EX times perpendicular distance. Let's figure that out. Perpendicular distance. So I'm gonna have to go back a little bit. This distance right here total. So it's gonna be 3 plus 5. Do you see that? That's a total of 8 inches from A down to EX. 8 inches. Okay. 8 inches. And then the sign out front, put my finger on A, pull in the direction of EX. It's gonna go counterclockwise. So that's gonna be positive. And those are all the forces causing rotation. So we set that equal to 0. Now, as we look here, do you see how E is our only unknown? Yeah, it's good. So go ahead and do your algebra here and let's solve for E and see what we get. Take it a step at a time if you need to. I didn't double check it yet, so if anybody got it and wants to confirm with me, they can, but I didn't double check my math yet. Did you? Okay, I only did it once, so I'm gonna try again.
Well, 260 divided by 4.4 cannot be 4.5.
Oh, it cannot, can it? No,
Is that really-
definitely not. So 260, maybe, did you get my other same numbers?
No. I think that we were calculating on 3 pages.
Okay, let me, again, I only did this once, so let's, let's ignore Kelly. What did I do wrong here? I thought I did times 4.33. Oh, I only did one of them. I only did one of them. And then it's gonna be, yep, I only did one of them instead of both of them. Yep, and then I didn't add the 4. So, oopsie, 8 times, and then plus, so it's 8.33. Is that what you guys got?
Yeah.
And then 260 divided by 8.33, 31.21. Yeah, thank you. What I forgot to do this one. If you'd multiply that out, that's the 4.433. So sorry about that. Yep. I didn't do both of them. That's why we check our work. It's good. Okay, it's a team effort. All right, now you can imagine 31.21 confirmed. We're going to take that E and we're going to plug it back up into, we have to do it in both equations because we need to get AY and we need to get AX. So go ahead and plug your value of E up into here. So I'm going to kind of keep this here in case you need to double check that. I'm going to do my AY first. You have the same. Did you get the same numbers that I did though? The 7, okay. And then did you get 4.395 for AX? 94, okay. Yeah. So I'll let you kind of catch up. You're gonna notice that with the directions that we assumed, your AY comes out to be a negative value, doesn't it? So what does that mean? That means that right now, we assumed up. But we never leave a final answer as a negative. So we're gonna make this positive, and we're gonna go up into our diagram. This is why we use pencil. We're gonna erase that direction, and we're gonna show it going down. Okay, going down. I check your final diagrams to be the correct direction. So if you need to make those adjustments, you don't have to recalculate to confirm it. We just do that 2-part process because that's the only difference, okay? So make sure that you make that 7.028 positive and change the direction to down for AY. Okay, so how did you do on your AX? AX is 4.395. That was a positive final answer. So that direction stays exactly the way it was. All right, that one was a little bit of work. This was our key here, right there. Putting our EX and EY in terms of its hypotenuse. That was really it. Any questions? These are kind of fun. I bet you're looking forward to doing the homework. Like, cannot wait. Like, thank you very much.
How much of the homework can you do?
Let's look. So what I'm going to do is I'm going to stop this recording here.